Okay, everyone, welcome back. Very excited to introduce our next keynote speaker, Thomas Kipf. He's a staff research scientist at Google Deepmind, working in the video generation team. And he has a cum laude PhD at the University of Amsterdam, working with Max Welling on topics like graph representation learning, introducing the very influential work on graph convolutional networks. And he also did a lot of important work on slot attention networks in object-centric representations for vision models. That's what he's going to talk about today. Do we need object-centric representations? Enjoy.
Thanks so much for the introduction. I'm really excited to be here. My talk today is about this question that I've been asking myself for quite some time. I've been interested in world models and just generally like building models that kind of simulate and model the physical world for quite some time. And there's this big question of like, should these models be informed to some degree by the structure of the physical world? And structure, of course, is like the key also behind neurosymbolic learning. And objects in some sense, if you stretch definitions a little bit, are like the symbols of the physical world, and like really the things that are grounded in our everyday environments. And so when you build world models, which are becoming ever more important, and we see like really cool examples emerging in the last couple of like weeks, months, and years, this question becomes very relevant. Like, to what degree do we want to kind of infuse structure into these kinds of models? And do these models need to know about kind of the structure of our physical world? Like someone on Twitter already, or on X, already tried to answer this question, Andrew Davison. He's a roboticist, and I think from a roboticist perspective, this feels like a relatively clear answer. I would want to take a step back from there, though, and like look at it from a broader perspective. And like in robotics, of course, like you kind of interact with objects all the time, and so objects are at the very center of what you do. But there is like a bigger picture, and I think it makes sense to kind of look back at the broader scope of like where things are right now with deep learning a couple of years ago, and now with frontier models, and like where the structure fit into this broader picture. And so that's going to be the theme of my talk, like basically structure in kind of deep learning and frontier generative AI, and at a specific example of world models, but like you can make very easy parallels to that to other models like LLMs and VLMs. Maybe the core observation, if you just look at the world around you, is that our world is highly compositional. So there's so many kind of reoccurring patterns, reoccurring like entities, and we can, of course, like to us as humans, it's very natural to reason about the world in terms of entities and their relationships. If you just look at everyday scenes, you can think of like agents, animals, cars, all of these kind of individual entities, and you can reason about their relations, what they're doing next. This Newton's cradle example here at the bottom, you can very vividly kind of imagine what happens next if you let time play out in this example. And so why should we care about objects? Well, objects are in some sense core to human cognition. There's a lot of work in cognitive science on that. That reinforces this kind of statement, but then also symbols, like symbols in some sense are like representations of like objects or other things, but you can also think of like symbols as being like reusable components of the physical world. Objects about being the symbols of the physical world in a kind of much broader sense, if you allow me to stretch definitions here a little bit. And so that is kind of the motivation for like why we should care about structure in the first place. Now, why care about world models? And what do I mean by world models? Like world models is like a term you see a lot these days. And to me, the definition is relatively simple. It's like basically a model of the physical world that allows you to A, simulate, and B, control what happens next. And so simulate just means like you either like roll out a particular possible future or a distribution of possible futures. And B is you have fine-grained control. You have some kind of control over what happens, and you can inject that control as time progresses. And so that definition covers a broad set of models, and we're gonna get there. But effectively, world models are mostly I mean, world models in like the literature, they exist like for a long time. Maybe the term world models, some people argue, maybe even came up before the term AI. But at the same time, world models in like modern machine learning, modern deep learning, really goes back to some of the more recent work, like this world models paper from David Hahn, Jürgen Schmidhuber, that went really popular. But then also like a lot of other papers that build on top of that, that effectively learn an action controllable video model of some kind of video stream. Like Dreamer, and often they're like in conjunction with agent learning, because world models effectively have often taken off as like models in model-based reinforcement learning, but they're a useful way beyond like just agent learning. So it makes sense to kind of, at least in my view, to decouple the sense of a world model from like this earlier definition that some people made in the RL literature. And so yeah, we've seen a lot of like progress over the last couple of years, and really like an explosion in the last couple of months. There were some really cool tech demos from models like Oasis, Cosmos, and NVIDIA model, and Genie 3 from Google Deepmind, just like a couple of weeks ago. And on top of that, other frontier generative models, if you look at that, they have properties of world models as well, like LLMs and VLMs. They can kind of similarly predict aspects of the future. They can be controlled in some sense and steered in a certain way to predict things you care about. Text-to-video models, image-to-video models also have very much like aspects of that. In a text-to-video model, you can essentially describe what action you want to take in language. Or in image-to-video models, you can even, some of these frontier models, you can draw what you want to affect in the environment on the first frame image that you condition a model on, and the model executes it. And even things like image editing models, you just produce, like you have a reference image and you produce a new image. But even that you can like view as like a snapshot of a world model. Like in order to instantiate an edit, you have to take an action in the world and then get another image out of it. Of course, they're not always grounded in the physical world, and they're always not always like physically plausible, but there's a sense of that in these models. And so the big question now is like, should world model builders, like people who develop these models, or just generally should we in the community care about objects? And a couple of the questions I want to touch upon today are, should neural architectures be informed by this compositionality? And that goes beyond like maybe the question for world models, and maybe the parallel for language models would be, should neural architectures be informed by symbolic compositionality? I don't really want to touch too much upon that. That's like for other people to think about, but especially for world models and objects, something I've been spending a lot of time on the last couple of years. And then should representations be structured in terms of objects? It's like a related question, but it's a slightly different angle. You can have structured representations without structuring the architecture necessarily. And then finally, the scaling hypothesis, like a scaling of data and flops given a particular powerful architecture, all you need, which is often also referred to as the bitter lesson. And so if you look back at like representation structure in deep learning, and I'm really going to start with deep learning here and like the big wave starting from 2012 and not really too much before that. So in deep learning, specialized architectures and representation structures for each data type were commonplace in the early days. Like you had like grids and sequences and graphs as data representations, and then very specialized architectures for each of those kind of data representations, like convolutional neural networks, recurrent neural networks for sequences, and graph neural networks for like more like complex structured data. Now, if you fast forward a couple of years, and that's like 2017 plus, which is almost a decade ago now already, generative modeling has really converged around across multiple domains along like one kind of new architecture and sequence structure and representation structure paradigm. And that was first obvious in language in 2017 with like the Attention is All You Need paper and work leading up to that. And that is so now obviously everywhere. But you have the same thing happening in visual data, starting with models like the Imagine model, the text-image diffusion models of deep language understanding, And then going forward to things like AlphaFold, where like the latest instantiations are effectively also just like big diffusion transformers. And so even though we have all this richly kind of structured data underneath, you see like a common paradigm emerging across like the architectures. And so representation structure in generative AI has really converged both in terms of like the structure of the representation itself to some degree and architecture. So in language, of course, you have autoregressive, primarily autoregressive transformers, so causally masked transformers over subword tokens, and how they exactly tokenize, of course, there's like many differences, and also in the attention patterns there's many differences, but that's kind of the core paradigm. For visual data, the predominant paradigm are diffusion transformers over visual patches, or like not just like visual pixel patches, but maybe even like more strongly encoded visual patches. But of course, like both for language and for visual data, you can also interchange these. You can have diffusion transformers in language, and you can also have autoregressive transformers in visual data. These are just like examples of like what's like mostly being used at the frontier these days. And then atoms and molecules, you can also just represent effectively as like a sequence of tokens, like encoded atom coordinates in the case of AlphaFold 3, and a few other extra side information pieces. And then you run a diffusion transformer over these groups of atoms without any 3D inductive bias. Like that just comes into the encoding of the nodes itself. And that's pretty remarkable that we kind of in the community at the kind of frontier went from like all these specialized kind of architectures and specialized structures to this kind of consolidation. This hasn't happened across the entire field though, and many, and myself included, have thought a lot about like, okay, what do we lose by that? Does it make sense to kind of structure things more around like some structural components of environments? Like, can we like we as humans, we even though we interact, like we have pretty generic kind of brains that absorb all kinds of like information about the environment, but yet we always learn about objects. We always like have like a very kind of succinct representation of objects apparently. And so the question is this something maybe that requires some more specialized components, or is this something that just like emerges from training? And so the big question is then, does this kind of representation structure still matter? And do we have to kind of build specialized architectures to get like these structural representations, or these frontier models, are there other levers we can pull? And so I'm going to get more into that in the context of object-centric learning, but even at the frontier with like just large language models and big transformers, you still have to think about representation structure a lot. So instead of enforcing special architectural constraints, which kind of used to be like the art of like developing these architectures, now the focus is more on like how do you tokenize, like what makes up the individual token? How do you construct the sequence of tokens that you feed into this model? There's a lot of like representation choices you can make, of course. How do you encode the position of those? That gives you a lot of invariances and equivariances. How do you mask, like how do you control information flow in the network? That effectively comes down to attention masking, which basically brings us back to graph neural networks, so transformers in some sense. And graph neural networks are very related. They're all message passing architectures, and as soon as you start controlling the information flow, effectively you have a propagation graph underneath. And so finally you also have data augmentation. The data itself, you can do a lot to it and augment and present in a certain way. And if we now look at visual models of the physical world, then this typically looks like the following. So the predominant approach for building like tokens for visual encodings is some kind of patch-based image representation. So you would start from pixels from, say, an image, and then you either first pass them through some kind of initial encoding stage, or you literally just take the tokens, the pixels themselves, take a patch out of those images and just flatten those pixels and declare those as your initial representations. Typically these days it helps if you do some encoding ahead of time, like really kind of a low-level vision, more like what a retina would do in like the nature analog. But in principle, like the core principle still mostly holds that like typically you have one token being like one square patch of your input, and usually you would patch in pixel space, but also patching in feature space, also very common. And finally, if you have video data, you would do something like spatiotemporal patching, and that's not just like interesting for representation learning and for these architectures to do something useful, but it's also kind of a constraint that like you almost have to reduce the information and spatial and temporal dimensions to some degree if you want to be able to feed this in these architectures, just because let's say you have like a long video at very high resolution, every single pixel would be a token, these architectures would be just way too expensive to run. So it's also to some degree a very pragmatic choice. And now that is kind of like the completely, let's say, content agnostic way of encoding the visual world. But then there's this other kind of school of thought that says, okay, maybe we can do better than that if we pre-parse the visual input and try to extract things like representations that are more aligned with like certain semantically meaningful pieces of the visual input, and then feed those as tokens in a transformer that then can compose and reason about these things. And that has led a lot of people to this kind of field of like object-centric representation learning, where you try to kind of pull out these kinds of representations and structure these representations more like explicitly and build particular architectures for it. And this can be done completely unsupervised or using human supervision. And so there is like, in this kind of representation structure, you can have like a number of different approaches to structure your representation. So you could, for example, just declare one object token to be one time step in your model, and somehow train a model like that at every time step it pulls out another piece of the input. And that's like the sequential slot paradigm. You can have spatial slots where you just say, okay, these are more like patches of your input, and you just discard the ones that don't have an object in them. Or you can have instance slots, which is saying you just have a set of, say, latent tokens, and they somehow map to the input. But let's say if the input is twice as large, you don't want to necessarily have twice as many latent tokens. So they can be really independent. I can have like just say 10 of these slots. They can capture objects in the input, irrespective of like what resolution you choose for the input image. And so these boil down to an ordered sequence of vectors, a grid of vectors, or permutation invariant set of vectors. And so I'm just giving a bit of a historical overview of what people have tried in this space. And so sequential slots were kind of one of the first to be explored in this area in object-centric representation learning. That was like starting before transformers, with papers like attend, infer, repeat. There was a recurrent neural network that would peek at the input image, extract one token out of it, and then feed that, or like one embedding vector out of it, feed that into a neural net, and then conditioned on that it would attend again into the input, pull one out, and then every time step you would basically attend to a different object, until you then train a model to say either reconstructed sequence or predict a certain downstream task. And Monet is a follow-up version that has a very similar idea, if you've seen that paper. I'm not going to go too much into the details of those papers, but just to give you a bit of an overview. Spatial slots have also gotten some popularity where they, as I mentioned before, they effectively boil down to encoding your image like in a patch-based model. So maybe you have a CNN, then you have your image patches or your feature patches, and then you just drop the ones out that don't have an object in them. And you just keep the ones that have an object in them, and then you just say, okay, here's an object. And so in this case, there would be 2 active patches, the ones in blue, and the rest is just free of patches. And then if you have an indicator variable that tells you object or not, then you can later interpret these like latent representations and see if the model kind of learned to structure the input in some kind of interesting way. And then finally, instance slots became more or less like the predominant approach, even though they were the latest to kind of start off, because they don't assume like a particular underlying grid or sequence structure. You can basically just say, okay, if you have a set of tokens, and a set structure is very nice because you can't really a priori decide like in what order you want to parse an input. Any kind of order you decide upon, you can find counter examples that would break that. And so it's like very difficult to figure out what like the ideal would be. And so and on top of that, if you define an order, you would also typically then want to kind of sequentially process the input. And any kind of sequential processing is slow, requires backward through time. And so if you can somehow do all of that in parallel and just populate a set of vectors, that's heavily preferred. And before I go into slot attendance, one example, just to dive a bit deeper into how this works, I just wanted to showcase what some of these models were capable of over the years, just by unsupervised learning, using the structure of the representation as kind of a bottleneck. And so you can have these models discover, like parse a scene into objects, even though you don't have any labels for it, and really decompose your input in a meaningful way, both for video data, for robotics data, for 3D data, and also for in-the-wild images. Now, there are some limitations with these models because there's a number of limitations. As soon as you start assuming that your world consists of objects, the problem of hierarchy arises. Like at what level of description hierarchy do you want to describe the scene? Like how many objects should there be? What about parts? What about groups of objects? And so all these things start to kind of hit you as soon as you start making these assumptions. And so it turns out for like simplistic scenes with a certain prior about how many slots you give the model, it captures like what is very intuitive for people. But like once you get into like more unconstrained settings, these models tend to struggle and tend to not give you what you expect. But just to dive a bit into some of the iterative refinement and instance slots methods. So the first paper that really nailed down one good recipe for that, and there's some earlier papers that I'm like mentioning here in the corner, like RC and Tagger and NEM, all by Klaus Greff, who was one of the key proponents of this area of research. So this particular paper assumes you have like a parallel and iterative process that encodes your image or your input at one time step, kind of parses it, and then decodes again. So every time step, every iteration in this iterative process, you would kind of make a hypothesis about how your scene is structured. And then given this hypothesis, you generate the scene again and compare it to the original scene. And then using this error, you feed that back and do another iteration. So that's very elegant because it kind of reasons based on like eventually converges to perfect reconstruction because you kind of minimize this reconstruction error as an inner loop. The downside is you have to encode and decode multiple times to get to your output, and that just made this very impractical. That's when slot attendant came in, which is a project I worked on with Francesco Locatello and a few other collaborators some time ago, where we tried to kind of embrace the core piece of a transformer, which is like the attention mechanism, but instead of using a big self-attention or causal attention block, we were saying, okay, you have your features, which are like the patches of your input image, and now we want to populate a latent representation that is structured into a set of objects. And now instead of doing self-attention between each token, like the tokens being the pixel tokens or the patch tokens, we said, let's just initialize a separate set of tokens. And these tokens we call object slots, and they cross-attend multiple times into the image tokens. And that iterative cross-attention allows the model to effectively pull out the right information. But we needed one extra trick to make it work. We needed invert the cross attention. So we need an inverted softmax in the cross attention. And the reason why this was needed is to not allow the model to put in all the information, or to redundantly encode everything. That inverted softmax effectively forces each pixel or each input patch to choose one of the slots to bind to, and it cannot bind to multiple ones at the same time. So each pixel needs to go somewhere instead of it being able to go everywhere at the same time. And that way, over these multiple iterations, just by self-supervised learning, the model kind of learns to route objects into individual slots, a bit like a clustering algorithm.
So why isn't it binary?
What do you mean by binary?
Well, you said the pixel has to go to one slot or a different slot, right? But the images aren't binary.
Oh, right. Yeah, this is an inverted softmax, so it's like a soft clustering, so we want backpropagation to work. You can binarize it post hoc by just making an argmax, but that would mean you would have to train it in a different way. That's a great question. It also raised it's like maybe one of the core questions in all of these is structure doesn't necessarily have to be to what degree do we want structure to be structure of a representation, a permutation symmetry, or like that kind of structure, like a symmetry structure, or to what degree does it have to be a discrete encoding versus a continuous encoding, or a discrete assignment. In general, I would say discrete encodings and discrete assignments are just very, very difficult to work with. And the only way you can make them work is to use reinforcement learning or to use some kind of approximation of the gradient. But these approximations tend to often push you in the wrong way or are difficult to optimize. And so my philosophy around these things is to not care too much about discreteness. But when I say structure, I really mean structure in terms of a set of tokens that have a permutation symmetry on them, or a spatial symmetry on top of them. So structure more in the sense of symmetries. Or compositionality, which doesn't require this discreteness in some sense. And so with this kind of architecture, you now can do just simple autoencoding experiment, and just by having this simple structure on the latent variables, the model tends to then learn this kind of discrete looking routing. Discrete in the sense that you have a set of tokens, but all the assignments are soft, but they really converge with high confidence. And so what you end up with in this experiment here is the model would automatically kind of route objects to individual slots, and then when you inspect each slot and decode each slot individually, in the absence of the other slots, you get the individual object reconstructed. And here I'm also showing the objects multiplied with their respective responsibility mask. That's why you see sometimes an object masked out by the occluder. But if you reconstruct it without that responsibility mask, you would actually see the entire object being reconstructed. So the model kind of has a representation of the entire object, even if it's occluded, which is kind of similar to how we as humans perform kind of amodal completion of occluded objects. Now, I just want to go a little bit over how to extend that to videos into 3D, and that is relatively straightforward. Here you can simply, once you have your slots, you can use the slots you discovered at one time step as initialization for this attention mechanism at the next time step. And that way they become consistent over time. Just more or less just a skip connection over time. And that way it's exactly the same architecture per time step, and a skip connection on the slots over time, which is symbolized here by this time loop. And you can train that, and then you get kind of temporal consistency and tracking of objects. You can also do the same thing in 3D. Here you would first try to get all your input representations into some kind of scene representation, and then just apply slot attention, and then decode back into your scene representation, or back into pixels. For the decoder now you need a camera coordinate as well, because the model needs to know which view you want to decode. And by separating out this camera token, you can now also get control over the camera, which is like a very elegant feature to have. And that effectively gives you instance slots or like object slots combined with novel view synthesis. Now, one project I want to talk about now, getting a bit more closer to kind of dynamic models and world models, is slot former, which is something, again, that's already almost 3 years ago, we've been working on to understand a bit more like whether these kind of structured representations really get you some kind of benefit for modeling the world forward in time. Like basically simulating complex physics in very highly compositional environments where you can really measure whether the model like generalizes to new compositions and to kind of new examples and really learn like the underlying physics of the scene. And so here again we would like apply slot attention at each time step with a skip connection to get all the individual components of the scene, and then have a simple, so once we have that pre-trained model that gives us these slots for all time steps, we would have a very simple block autoregressive transformer. And block autoregressive here means it encodes everything at the same time, all the past history, but every single time step, which is say a set of 10 tokens for every time step, which could be the 10 objects, can only attend to tokens in the past, but not into the future. And that gives you like a block causal structure. Like if you look at the attention matrix in this model here, it would be a block diagonal attention matrix with a block size of how many slots or how many tokens you have at each time step. And that's a very important class of models because it effectively gives you a causal model that you can bring forward in time, but it's fully parallel over each time step. And so that is a very kind of nice model to work with, and we worked with this model in the context of individual object slots. And then once you decode object slots one time step, you can just feed them back into the next time step and decode again, and that gives you like a video model that is informed by the structure of the underlying world. And so that model was doing extremely well. Like it really solved this task of these very simple kind of block scenes very easily. But again, the problem here arises like once you want to scale this to like the physical real world, this dilemma that I mentioned earlier of like how do you actually decompose the world into a consistent set of objects kind of comes back. Like what if like the right abstraction level to model a certain thing is not at the object level, but like at the group of a certain number of objects? Like let's say you want to model a bird swarm or fly in the sky. Maybe you don't want to model every single bird, but you want to model the entire thing as a group. Or you want to model a car, but then you might want to model like the individual components. Maybe someone's opening a door. Maybe it's easier to simulate that if you just had represented the door as its own component. And so the model doesn't know about all these things. And so this kind of type of architecture that enforces a bottleneck to learn a set of object representations turns out to be very hard to scale. Doesn't mean it's impossible, and it doesn't mean that this is maybe not the right way forward. But the community has sort of had a hard time going from these examples we've seen here now to really something that solves world models effectively. But then there's the other question just around like, so this was more about like simulating, predicting the future. But then another angle is like controllability, like how controllable are these representations? And one way to ask the question is to look at the representations themselves and see if they're useful for robotic control tasks. Like can you read out representations that, or can you read out tasks from them that require manipulating the environment? And the other is, can you manipulate those representations themselves to manipulate the environment if you decode that? And for the first question, there was a really nice paper, Palmi, that effectively had questions and images about a robotic environment, and then a large language model that would predict the action you would have to take, or like an action plan that you would have to take. And in that paper, what my collaborators did is to not just inspect what happens if you put a vision transformer in there, which would just be a patch-based representation of the image, but what would happen if you had your representation of the environment already pre-segmented into object tokens using one of our slot attention models, and feed that representation in. So now the model directly gets structured tokens where each token corresponds to one object as opposed to just a patch-based representation. And we were wondering, like, does that give you any benefit for these kinds of tasks? And so the answer is kind of yes and no. It does help you, and the bold numbers here are in favor of OSRT, which is the object-centric representation. It does give you a big boost in a very low data regime, but then that benefit tends to disappear as you scale up your data, which is not shown in this figure, but if you look at the paper, they have a plot in there. And so that is maybe one of those lessons. So these kinds of representations tend to be really or something really interesting happens around data efficiency with like structured representations and objects. And that's maybe the right angle to think about it. Whenever data efficiency matters, it might be worth thinking about these kinds of like more like structured, highly structured architectures and representations. And now it's an open question of how to keep these benefits at scale, or whether these still matter. And the other question is like, how do we control things in environments that I mentioned? Like, let's say you want to build a world model where you can now control every single thing in an environment. And there is still one piece missing that I haven't talked about yet. So even if you have an object-centric representation, you don't automatically get like fine-grained control over the environment. You first have to figure out how do you actually assign actions to these individual representations? How do you manipulate them? If someone gives you like actions in the real world, how do you map those actions to those representations of these objects? So there's like kind of a matching problem, and also like a compositional learning problem. And that is something that ultimately got me into this whole kind of world modeling and object-centric learning direction 5-6 years ago, which led to a project called Structured World Models, where we try to kind of do both at the same time, like figuring out with like very simple architecture at the time, like how can we learn like in a fully unsupervised way, learn from just like video data or interaction data, learn a model of an environment that doesn't just give you representations of objects, but also individually manipulable representations of these objects, so that you then, if you intervene on one object, you can control that one object and make it move in a certain way, or like whatever the action is in the environment. In Atari games, like move a character, or move like the other character that's also in the game, etc. And so that turned out to be very, very difficult at that time, so that like the object-centered representation learning approach, these methods were not really mature at that time, but then after spending a couple of years like developing slot attention, these methods, we decided to go back to that problem and think a bit harder about controllability. And the problem with like object slots, if you take them from these architectures, they're just unstructured vectors. And so there's not a lot you can do to actually control what happens in the environment. There's like very simple things. You can just delete one of these vectors, and then the object would disappear. Or you can swap these vectors between two different scenes and recombine them, basically, or recompose these vectors. And that gives you another interesting kind of edit or action in the environment. But these are still very, very simple and kind of boring actions. But that's the first thing we looked at, what happens if you train a model that you can actually then do these kinds of edits to. And so we trained a model, and that's when we slowly started getting into diffusion models, just because they are much more powerful generative models. We trained like a video diffusion model architecture on street view data, and then had like a slot bottleneck in their representation. or conditioned on object representations that we learned separately. And then you could delete these individual representation pieces and like suddenly a car would disappear in the scene that you condition on, which is kind of cool because the model has never seen that particular scene without the car, which is very surprising to us at that time, that you could just manipulate the representation and you really get control over these individual pieces, like an individual car, that it can make disappear. What surprised me even more is that you could take a representation of like, in these synthetic scenes down here, you could take a slot from one scene that encoded this little toy car and put it into another scene with a different lighting condition and render that scene again. And that car would be rendered in a correct spot, but under the completely new lighting condition with like the shadow and everything rendered correctly. Which now with like modern image editing methods, like very obvious thing that just happens in these models. But that was the first time we were seeing that, and that was like really really mind-blowing that the model learned apparently a representation that is completely independent of the other factors of variation. And you can recompose them, and the model then just renders it in the correct way. Even though there's no rendering component in these models, there's no kind of notion of 3D, it's just a big diffusion model. The main problem is though, like this is still very limited. You can kind of delete and then you can move and recompose. But ultimately you really want to go beyond that. And so that is what inspired some work that I'm personally very proud of is neural assets. And there we go from object slots and make two main changes to that. So first of all, instead of just having a single vector per object, which we had before, just very constraining. And it also gives you this problem that you have to make a decision of at which level of abstraction you have to model something. Because you have no internal compositionality anymore. We go to a sequence of vectors of any length for an individual object. And now you have internal compositionality because you have a set or a sequence of vectors that you can, in principle, also recompose internally. The appearance encoding is now distributed over this entire sequence or set of vectors for each object individually. And on top of that, we also wanted to separate action variables. In this case, the easiest action variable you can think of is like where something is in space or in an image. That's something that's very easy to annotate. Like object detection, we did 3D in this case because we found it interesting to see if you can really make like world-centric actions in a completely flat diffusion model. And so we separated out the appearance encoding into a set of vectors, but also like the pose encoding. And that's what we call a neural asset. It's a bit like an asset in computer graphics. And now the question is, okay, you can structure representation that way, but how do you learn that now from data? How do you get this without like building synthetic data generators for every single possible pose and every single combination of things you want to understand about the world? And I'll get into that solution in a moment. And I think that was like for us a big breakthrough that really clicked things into place, and why now I also believe that like general kind of image editing is really possible at scale with like paradigms like these. For example, you can given a source image with multiple objects, you now want to learn a representation of each object in these environments, and but then you also want to manipulate them in a physically possible way, which are kind of the edits you want to do. And these edits can be, you want to translate every object, you want to rotate them, you want to rescale them, even though you haven't ever seen like that particular arrangement. And here we rotate and translate and rescale them all at the same time, but that's just like for visualization. You really have control over every single piece individually. And that is what we call like neural assets or multi-object 3D control from a single source image. So the input is literally just the image, and then the model learns this, like extracts this representation, and you can start controlling it. We were inspired by computer graphics workflows because their objects or assets are very much at the center, and you have some interesting actions which allow you to compose them. Like you can animate these assets, you can put them in a scene, and you have all this kind of compositionality of the real world rebuilt in these graphics engines. And we were thinking, okay, like what if like just a deep neural net could learn to be a graphics engine effectively on real data? which is like the first step to kind of building a world model, because ultimately you can think of like a world model as a big neural net that acts like a game engine or a physics engine, all these kinds of things at the same time. And so one important piece is like 3D assets, and in computer graphics, these are reusable components, hence also like a bit like symbols, that have some associated information with them. For example, appearance information, a 3D shape and texture. And you can assemble scenes and worlds by putting them into a scene and manipulating the pose. And so neural asset is effectively the neural counterpart of that, just a representation, just a set of vectors that encodes appearance and pose information. And pose is really like more like the action component, and appearance is like the essence of the identity of the thing. And so the main challenge here is, how do you learn a representation of environment that captures all these things? Because you just don't have enough data that has like paired images where in a source image you have one car in one rotation, in the target image you have exactly the same scene, but then maybe the car in the other rotation. And that data just doesn't exist. And it's also like impossible to collect for everything at scale. And if we were to resort to computer graphics approaches to render the data, then our performance ceiling would be computer graphics visual performance. And so we want real world data, but we need a different approach to be able to kind of learn all the possible edits. And so the nice thing about video is that you see all these edits happening, but they all happen at the same time. So when you just look out in the world, everything is kind of always changing at the same time. You hardly ever have like isolated changes. But the nice thing is you can annotate all these changes. You can annotate all the things at the same time compositionally that are changing. And then if you structure your model just in the right way, it learns kind of the components of all these things that change at the same time and pulls out just the right one, so that at like inference time you can just manipulate them individually. Like you can. That's kind of the beauty about this compositional approach here. And so the other part is like, how do you disentangle appearance and pose? So how do you disentangle kind of identity and action? And that's the other challenge here. You want to encode these from like two different frames. So you want to have like a source image and the target image, and you want the appearance to be encoded from one of them, and the kind of relative action, or the pose in this case, encoded from the other one, so that the model cannot just cheat by auto-encoding and putting the wrong information in the wrong structure. And so the way this works here is we give the appearance from the source image the relative pose change by the target image, and we only ask the model to reconstruct the target image. So the pose is kind of the edit instruction, and the appearance is the identity of the thing, and then the model has to then reconstruct the target image. And so we annotate this data with like this compositional annotation. Like we tell the model, okay, in this target image here, these cars like moved by so much and they rotated by so much, but we don't tell it like, we don't give the model like an encoding of these images. And so the appearance ends up being pose invariant. Like the model learns like an appearance of the entire asset, irrespective of like from what angle it is seen in the first frame, and it can then reconstruct it under all possible kind of angles. And in practice, how we do it is like we encode like just a small image region within that patch. Like we extract kind of like within the source image just where the object is. We extract some representation from it. And the target image, we encode the pose, which is just like a bunch of corners encoded, like target, like XYZ variables of where the corners are of the bounding box, encoded into a vector. And then we just serialize all of this information, the sequence of tokens, and feed that into an image diffusion model. And so the nice thing about image diffusion models, or just general text-to-image, text-to-video models, they typically always have an API where you have a sequence of tokens that you condition on, because they typically like are built to work with textual encodings. And the nice thing here is you can just like, in addition to the text or you can swap out the text with these like asset tokens, and the model just learns to interpret that information and then render the image given that more like asset-centric description instead of a text description. And one final thing we do is we also encode like a global view of the scene where we mask out the foreground objects, basically the ones that are detected. That masking is not super critical. The model also tends to work if you just give it the full one. But that helps the model encode both the objects and the scene overall. And so at test time, we can then rotate assets, we can replace assets between scenes, and we can really act upon each asset individually. And so these are a few examples that you've already seen teased in the first few slides, but it also works with like completely new lighting conditions. Even if a car is like not fully visible in the first frame, it still has a full representation of it and can put that car anywhere in the scene. It also works in other data sets, like indoor data sets of like 3D objects or objects. These are just videos of objects annotated with 3D boxes, and then we can rotate these objects and translate them. Here, the background in this case is not annotated, and so we don't have like a good separate representation for that. So often these are a bit entangled. But as you scale these things and have better annotations, this entanglement like would usually not be an issue anymore. And so finally, you can also just drop objects. You can isolate them. You can replace them. You can recompose scenes. And one thing that impressed us most is you can also take a different background from a different scene and change that out for these cars up here at the top. So these cars are always the same, but then we swap out the scene background. And if you swap in the night background, the model learns that now these cars have to be rendered in kind of a night environment, and they even turn their headlights on when they're on the street, and when they're parked, they don't turn the headlights on. So this is kind of a fun thing the model learned about these environments, just via this kind of compositional representation. There's some failure cases. These are like limited data sets, and there's some issues around canonical representations for orientation. So the handle here doesn't make a full 360-degree turn, but only 180-degree turn. Sometimes the cars tend to be sticky to lanes because the model hasn't seen too much off-lane driving. And the model can do things that are too far outside the training distribution. It's not a generalist model. It has been trained independently on this object data set and independently on the car data set. And so you can do things like lift upside down or flip a car upside down or lift into the air. We've recently worked on extending this and trained this on a bit more general data sets. This is soon going to be in the archive. Not going to go too much into detail here, but like one thing we've always thought is like, okay, this shouldn't just be edits around poses, but you can also pack much more action or edit information into these latent variables. You can also encode things about shape or the geometry of an object. And you can really then have like a representation, a structured representation of a scene that is a bit like a universal scene description that people use in computer graphics, but then one that interfaces with diffusion models. And not going to go into details here. It's hopefully in the archive very, very soon. But you can effectively then condition on like the shape of an object and let the model imagine the colors, or you can swap assets again between scenes, and you can perform multiple edits in conjunction, and then in the latent space or in the scene space, and then decode every time to see what the effect had. So you don't have to, like with classical image editing models, you would have to make an edit to your image, decode, and then encode the edited image again, and so artifacts tend to accumulate. Whereas if you had like a latent structured description of a scene, you can make all your edits in that structured description and always just decode. So you would never have to kind of go back and forth between encoding and decoding, which is what typically gives you artifacts. And now before concluding, I just want to briefly go back to video models and world models, and where like some interesting emerging direction that has happened in the last couple of months. There's one paper that just recently appeared in the archive that I find very interesting. It's a paper that manages to fine-tune a video diffusion model using a bunch of object image data. And the interesting thing is they train this model purely using in-context learning. So there's no architectural constraint, there's no structural constraint. They literally, these conditioning images, they literally encode just as video frames earlier in the video. And they take a pre-trained text-to-video diffusion model and just then fine-tune that model on just 40 examples of pairs like images and videos. And then the model picks up this object compositionality from just that in-context learning. So there's no representation structure trick here. There's no architecture trick here, no object-centric encoding, and yet they can, at test time, place like entities from reference images into new videos, into context. And so that is very fascinating because like we've kind of seen now over time how things have shifted from like architecture engineering to more like representation structure engineering, representation learning, all the way to pure in-context learning of like large frontier models, and how in an extremely data efficient way, in their case of just 30, 40 examples on a single GPU, fine-tune like this, I think a 5 billion parameter video model, to get like a really interesting capability like that really requires you to understand something about objects and scenes without any structure. And so that I think, that's a paper I can recommend reading. I'm not going to go into too much more detail, but that is like, I think, a nice kind of conclusion to go back to our original question, do world models need objects? And so my answer to that would be both yes and no. Like we've seen over the years now a bunch of examples where you can learn something really interesting about environments and the world by having particular architectural constraints. But as you scale, the need for these tends to diminish and tends to go down. And all of a sudden you can pull out really interesting capabilities of these frontier models just by some smart prompting effectively and with a little bit of fine tuning. And so these models have something, like in order for a model to learn like a general object placement composition capability with just 40 samples, it has to understand something about object compositionality in its way it's just pre-trained from just generic data. And so that is, I think, like a very interesting research direction to just like think less about like the structure of the architecture and representations, but really like what is already in these frontier models, how can we find better ways of pulling this information out via some really smart ways of kind of fine-tuning them. And so yeah, early successes were really enabled by architectural constraints, where like the community has focused more on explicit model internal object representations, and we've seen a lot of successes with that, but also like these things typically have hit like a really big ceiling that's hard to overcome. But then modern frontier models clearly have some object level understanding and capabilities. They can like model physics to some degree, they can memorize the geometry of a scene, they can recompose information about the environment, and they can do that without any object-specific architectural constraints. And so that's very interesting. And so maybe the final takeaway from this question here is like that object-level control, if you really care about controlling things in the environment, that really still requires some specialized kind of approaches, because it requires object-level information, like annotations, language descriptions, reference images, but you don't really get that at scale from just like observing raw data. So you have to be smarter about this. And so should neural architectures be informed by object compositionality? Well, compositional architectures scale really well, but they're not necessarily compositional exactly at the object level. They can be, but like even if they're compositional at the patch level, they tend to eventually learn about objects. And I think that's like the very important thing the community has over the years realized. So you don't necessarily have to enforce this constraint that one token equals one object, or one group of tokens equals one object. But these compositional architectures, they can figure out the right grouping if it's needed within the architecture. And then finally, should representations be structured in terms of objects? I mean, all these are open questions, but I'm just giving some opinions here. In terms of model internal structure, I would say it really depends these days, just given that we've seen like so much progress on more like unstructured but generically structured frontier models. But at the input level, I would say very much yes, if you want to control individual objects. Like even in this example of this in-context learning, the input is structured. They effectively kind of use temporal slots for objects. Like they use a particular time step for presenting a particular object, and they go to the next time step, present a particular object. And so they structure their input in a particular way. And then finally, is scaling of data in flops all you need? Well, controls and actions don't come for free. If you want to learn these controls, you gotta annotate this in some way. And there's just enough, there just isn't enough paired data of isolated object changes. So you need more creative solutions. But of course, like the whole scaling paradigm is like underlying most of the progress in the space. So where do we go from here? I think one really interesting direction is data efficiency as a research frontier, which of course many are thinking about. Like what enables fast learning of these object-focused capabilities? And this in-context learning paper I've shown you is like a really great example of that, because it was an academic project, a single GPU. They've, with LoRa, fine-tuned with just 40 training examples for like less than a day, frontier video model, and enable an amazing capability. Like that's just very impressive. And that's something a single researcher with a single GPU can do. And then the other thing is like, how do you isolate action components, like a single object change at scale, even though in the world, if you have video data, everything changes all at once. That's also like one of these very important questions, I think.